All right, let's quickly look at energy of a charge capacitor, that is the derivation of the energy in a charge capacitor using the integral method. Now, if you talk about energy of a charge capacitor, a capacitor actually is a device for storing electric charges. We've said that before. And when you talk about a charge capacitor, you have this sketch above shows a charge capacitor, the plate of a charge capacitor with charge Q and potential V, with an additional charge, increase in charge, which is a very small charge, a little increment in the charge, the Q here, and you have the other part, a little increment in the potential, the V. So at this point, we can talk about the total work done on this charge capacitor, or that total work done again is still known as the energy stored in this charge capacitor. And then when we want to do that, we look at the total integral from the lower limit of this charge parallel plate capacitor, of this charge plate capacitor, to the upper limit, which is the total charge from 0 to Q of this charge capacitor. Then we multiply it with the product of the potential and the change in Q. This little increment in Q will be multiplied by potential. Then we'll look for the integral of that from 0 to Q. Now, total work done is energy stored, which is integral as we go from the lower limit 0 to the upper limit Q, which is V dot the Q. Take this as your equation 1. Now, but capacitance of a capacitor is defined as charge on either plate to the potential difference across its end, which is Q over V. Therefore, at this point, you can make V the subject of formula. If you cross multiply, we are going to have that as Q over C. Put this Q over C into this equation 1, and we are going to have the energy stored, which is still the work done, which you can just represent with W if you want to use that, or you use energy E. We are still saying the same thing, is equals to the integral as you go from 0 to Q. Now V here has turned to Q over C dot the Q, the little increment in the charge. Now at this point, we cannot integrate charge with respect to capacitance, so we need to bring the capacitance outside the integral. So if we are going to do that, let's go to the next page. That gives total work done, which is energy stored. We now be integral, bring out the C, so is at the denominator, it becomes 1 over C out of the integral sign as you go from 0 to Q of, you are left with now Q, which you are integrating with respect to the Q. Now here we can have work done, which is still same thing as energy, which is 1 over C. So we want to integrate this charge Q. If you want to integrate charge Q, note for integral you have x raised to power n plus 1 over n plus 1. So this n here represents your Q, and this n here represents the charge that you have, or the number that you have on this. This is like Q raised to power 1, that becomes 1. So here now you can have this as Q 1 plus 1 over 1 plus 1. So keep this. So integral of that, now when you are integrating, we remove the integral sign, so you have something like this. Integral of Q gives Q squared, which is 1 plus 1 over 2, but you move from what, the lower limit to the upper limit, which is Q. So at this point, work done, or the energy stored, will be 1 over C, which is still outside. Now this Q squared over 2 is what you have after the integral. This little q, small letter q, we take the value of this capital letter Q. At the same time, the small q, we take the value of 0. That means it will become 0. So at this point, what we are dealing with now is, we are going to have something like this q becoming the capital Q. That gives Q squared over 2. Now this is a determinant sign, which means a negative of what? 0 again squared over 2. Close that. Now this part turns to 0, so you have work done equals to 1 over c of, you are left with q squared over 2. So which you can open the bracket as, this will be q squared over 2c, and that is still same thing as 1 over 2 q squared over c. Now but q, which is charge, is cv, so take this as your first equation for energy stored in a capacitor. So we add equation 1 the other time, this becomes equation 2. So anywhere we see q now, we replace q with cv, that is, bring this into this now. So if we do that, we are going to have work done again equals to 1 over 2, in place of q it becomes cv, but this is squared, over c, and that gives 1 over 2 cv, that means c squared v squared, right, over c. C here cancel one of this c, so you'll be left with 1 over 2 cv squared. Take this as your what? Second equation for energy stored in a charged capacitor. Okay, so similarly again, we had it the other time that, but again you have q equals to cv, right? So we can decide to make v the subject of formula, but recall that the first equation we got after the integral was work done equals to 1 over 2 q squared over c. So we've substituted the value in for q, so we need to substitute a value in for c also. So how do I do that? Make c the subject of formula here. So that means c becomes, here you are going to have c now becomes q over v. Put that q over v again into our equation 2, which is this. So you have it that work done again equals to 1 over 2 q squared, anywhere we see c it becomes q over v. That means this is 1 over 2 q squared divided by q over v, and then we have work done to be 1 over 2 q squared times v over q. Q cancel one of this q, so you are left with work again is 1 over 2 qv. Call this your third equation, which will now be our equation 4. Therefore, for energy stored in a charged capacitor, you have the following formula: energy now stored in a charged capacitor, that is using the integral method. You have the first one, this is 1 over 2 q squared over c, or you have it as 1 over 2 cv squared, or you have it as 1 over 2 qv, and that gives the summary of the energy stored in a capacitor. Application of all this formula depends on the parameter that is given to you in a particular question. So if a question gives you charge and capacitance, you can kindly go with this first one, or you have charge, capacitance and potential, you can go with this next one, or again you have charge and potential, you can go with this next one. But nevertheless, any of this formula could still be used to solve any problem that is given to you, provided that you are able to navigate your way out from this part where you have it as q equals to cv. So whichever value is not given here, you can get them from this and then substitute back into this formula. That gives you the energy stored in the charge capacitor.